Alright guys, in this video what we're going to be taking a look at is using completion of a square in order to rewrite a quadratic function from standard form, okay, into vertex form. And so what I really mean is that we're tending to get things that come in this nice standard form, ax squared plus bx plus c. But what I want to do is I want to be able to rewrite this into, of course, vertex form, which is this a times the quantity x minus h squared plus k. And the reasoning behind this is because, of course, it's pretty easy to identify the vertex in vertex form. We recognize that it's just this hk because of our left and right translation, up and down translation. And also that our axis of symmetry, when we talk about a parabola here, of course, runs through the vertex, so it's this vertical line that passes through the very same x value at our vertex, or at x equals h. So the benefit to having it in vertex form is it pretty much declares where the vertex is, whereas if you're in standard form, we have to do this mess where we say, well, then my vertex is at negative b over 2a and f of negative b over 2a. So in order to avoid having to do this, which isn't a horrible thing, what I want to do is practice just completing the square in order to make this into vertex form. So we're going to do the same kind of procedures that we've done in the past with completing the square, except for what I want you to recognize is that instead of a number on one side, we have just a y value, or like y equals this amount. So I'm going to use f of x in place of y. Of course, they mean the same thing. But let's go ahead and start with our completion of the square. What we're going to do is we're going to boot this constant, this loose constant on the right side, and of course we're going to place in its place the constant that we would rather have. So if I were to subtract the 19 over to the left, we'd have f of x minus 19, and what this would be equal to is x squared minus 8x. Now, normally, I'd want to stop and check to see if our leading coefficient here is 1, and it seems that it is a 1. So since that's the case, what we're going to do is we're going to put in our last position here, this plus c here, that would be the value that would make this a perfect square trinomial. And of course, if we wanted to have that, we would just do half of our middle term squared, since we're in this x squared plus bx form. So half of a negative 8 would of course be a negative 4, and negative 4 squared is a positive 16. So let's go ahead and do this. We're going to add 16 to both sides of this equation. The fantastic thing is that the right side, of course, would fold down into this, and we would have half of our middle term here in this factored expression. Now on the left side, this positive 16 and this negative 19, what that's going to do is combine out to give us a net difference of a negative 3. So as we look at this expression here, all we've done was move the undesirable constant out of the way and then add onto both sides the desirable constant in order so that this would factor into a square of a binomial. We're very nearly into this vertex form. The only thing we seem to be missing is having y isolated and having our loose constant move back over to the right. So what we're going to do is we're just going to send our 3 back over to the right side here, and what we end up with then is just f of x, and it would be equal to this quantity x minus 4 squared, we would say plus 3. So now the nice thing about this is we can very, very clearly see the values of a, h, and k. So our a value here is 1, our h value is a positive 4, and our k value is a positive 3. Remember, your h value looks backwards, but it's not. So our axis of symmetry, the very first thing we want to write down is the x value of our vertex, or the x value that our axis of symmetry runs through. They are the same x value, but we say x equals 4. And then our vertex would lie at the point 4, 3. So just to kind of show you this here, I'm going to get my calculator rocking. Let me bring this over here. And what I'm going to do is I'm actually not going to graph the vertex form equation. I'm going to graph the standard form equation to show you that we do indeed get the same thing as we do in vertex form. So we get x squared. We have minus 8x plus 19 minus 8x plus 19. So when I graph this, we're expecting to see this thing that opens upward. Our a value was 1, and it has the same width as our parent standard quadratic function. But we see here that we go 4 to the right and 3 up, and this definitely is shifted 4 to the right and 3 up. So very beneficial thing, completion of the square, when you want to rewrite something from standard into vertex form. So let's try this again here. I've switched the name of our function to h of x, not that that matters very much. But the first thing we want to do is we want to subtract this 37 from both sides. So we end up with, excuse me, h of x minus 37 equaling this x squared plus 12x on the right. Excuse me. So the question is, what would we rather have as our constant to make this into a perfect squared trinomial? And again, it's always going to be this half of our middle term squared. So since I want a c value that is half of my middle term squared, I'm just going to write 12 over 2 squared, which is 6 squared, which gives us our 36. So adding 36 to both sides here, the neat thing, of course, is we've completed the square here, and so we get this squared binomial factored expression. And in here, we would say that we would put half of our middle term, which was that 6 that we squared to get the 36 in the first place. On the left side here, when we combine our positive 36 and our negative 37, that is a net difference of -1. And the last thing that we're responsible for doing is just setting this constant back over. So our vertex form, within 2 steps we were able to find it. We get x plus 6 quantity squared plus 1, meaning that our axis of symmetry, which runs through the vertex and has the same x value as our vertex, would be at x equals -6. And our vertex then, that vertex point would be at h and k, which is at -6, 1. Pretty cool. Cheers.